This video is the first in a series of 3 about numerical solution of ODEs. This video is based on my example script example damped harmonic. Let's set a breakpoint in line 2 and start the script. The usual initial settings. Now how can we pass the equation of the harmonic oscillation to a numerical solver? This first requires that the second order equation a times y double prime plus b times y plus cy equals 0 in line 6 is converted to a system of two first order ODEs by the following substitution. y1 equals y and y2 equals y1 prime. In line 8 we see just a definition of y1 prime, it's y2, and in the second equation in line 9 we now solve the equation of the harmonic oscillation in terms of y double prime. Now y double prime is y2 prime, so we have the equation y2 prime equals minus b y2 plus c times y1 over a. So we have solved in line 6 for a double prime. Now we have two first order equations, and the right hand sides of these equations are now saved in a function handle which contains a vector, a column vector of two functions. So if you have a look at line 11, then we see a definition of a function handle dy dt that depends on t, y, and the three parameters a, b, c. The first entry in this vector of two functions is the right hand side of equation 8, just y2, and the second entry of this column vector is the right hand side of line 2. So it's minus b times y2 minus c times y1 and over a. So this defines the way of computing the right hand side in the system contained in lines 8 and 9. Now this process can actually be automatized for a large class of ODEs, certainly for all linear ODEs, and we can proceed like this. First we write down the equation again in symbolic form, like in the previous video. Then we invoke the function reduce differential order. This function generates now two equations in two variables, in two unknown functions, which are called y and dyt. We convert this system of two equations, which are both first order now, to the so-called mass matrix form. We solve in terms of the first derivatives, and we convert to a function handle using the function OD function. And this function handle is basically the same as the one we have defined before manually. Let's make a comparison. The function handle dy dt also depends on 5 variables. So if you compare the two function handles, t corresponds to t, y corresponds to in2, and a, b, c correspond to param 1, param 2, param 3. Apart from the change in notation, these two function handles do exactly the same thing. So we can pass either of them to the solver. Now the solver has of course options, and in this case we set only one option. We set the maximal step size in t, in time, to 0.01. The time interval spans from 0 to 10, so we start at t equals 0 and stop at t equals 10. We choose one of the solvers that are available. ODE23 is a popular solver for non-stiff differential equations. It's a low-order method. There are also higher-order methods which are even more precise. And we see in the script how it is called. We now loop over 6 different examples. The first one is an undamped oscillation. So A equals 1, B equals 0, C equals 2. These are the coefficients. The initial conditions are 0 for y and 1 for y prime. They are contained in this column vector. And now we call the solver ODE23. Now the first argument of the solver is just the function handle dy dt. But we have to be careful because dy dt depends on 5 arguments, and the solver expects a function handle that depends only on t and y. So we convert this function handle to an anonymous function handle which depends only on t and y using the current values of a, b, and c. So this is the first argument to the solver. The second one is a time span. The third one are the initial conditions. And the last one are the options. So there are numerous options. We have set only one of them, the maximum step size, to 0.01. Now the solver is executed, and we have a structure called sol as the result. This has various fields. You see which solver was used in order to compute this solution. We see what's important for us is sol.x. These are the values of the independent variables. And sol.y is a 2 times n array which contains the solution y in the first row and the derivative y prime in the second row. We store the x values in the vector t. We store the y values in the matrix y. We also have some statistics. This is contained in field stats. Here you see the number of steps that have been taken by the numerical solver, the number of failed steps, and the number of function evaluations. So the function handle passed to the solver has been invoked about 3,000 times, about 3 times per step. Now we can have a graphical representation of the solution. So we first plot the solution y, then we plot a y prime, the velocity, and we put some labels, a legend, and the title string. So here we see the solution in blue and the velocity in red. This is an undamped harmonic oscillation. Okay, let's go on to The other examples, a weakly damped oscillation. I will now put a breakpoint in line 63 and just go to the results. So this is a damped oscillation, weakly damped, so it oscillates, but the amplitude decays exponentially. Let's carry on to the next example, which is strongly damped. There are three different types of solutions. This one looks like this. So it rises in the beginning and then decays exponentially. The red curve is again the velocity. Strongly damped, different initial conditions, different type of solution. This solution decays exponentially from the beginning. A third type of strongly damped oscillation, again with different initial conditions. And this solution passes through zero and then converges to zero from below. And finally, we have the limiting case between weak and strong damping. In this case, we have b squared equals 4ac. So this is a limiting case, and this is the form of the solution.